So in our last video, we talked about the different decay types. I want to remind you it all comes from binding energy. You look at the binding energy of a nucleus, and if it's got more binding energy than its neighbors, it's probably going to be a stable nucleus. All the stable nucleuses fall on this band of stability. Each dot represents a stable isotope. And the key thing to remember is if you have too many protons, one of the protons will turn into a neutron. If you're on this side, you have too many neutrons, and one of the neutrons will turn into a proton. Then if you're way out here, you just have too big of an isotope, and that isotope will decay by giving off an alpha particle. That was our alpha decay. So today I'd like you guys to learn how to write the equations. So let's go back to polonium-210. Let's find polonium-210 on your isotope sheet. It says it's got an atomic number of 84 and a mass number of 210. So you start polonium-210, 84. It decays by giving off an alpha particle. You can see that in your isotope sheet. It's got the symbol alpha under decay mode. An alpha particle, as I mentioned the other day, is 2 protons and 2 neutrons. So that turns out to be 4 particles, 2 protons, and that's a helium-4 nucleus. Then you got to figure out what particle remains after this alpha particle gets shot out. And the way you do that is quite simple. You make sure that the charge is the same on both sides. So I need a charge of 82. So I have 84 on the left and a total of 84 on the right. Up top, I have 210 to start with. So I would need 206. What is element 82? It turns out that that is lead. So this polonium will have turned into lead by giving off an alpha particle. It will have turned into a more stable nucleus. And in fact, if we look at lead-206, it doesn't decay at all, so it turned into a perfectly stable nucleus. This is one where we had a neutron turn into a proton by shooting out a small negative charge that we call a beta particle. We said it was an electron that was ejected. So there's lots of things that beta decay. And the one I think I'd like to have you guys look at would be carbon-14. So we find carbon-14 on our isotope sheet. We write it out, 6 positive charges, 14 total particles in the nucleus, and carbon is the symbol. It gives off an electron, and here's how you write an electron. It has no particles of mass. The electron itself is so small that we don't consider it to have any massive particles, so there's no nucleons. And it's got a charge of -1. So anytime you have beta negative decay, write it like that. Again, the symbol for beta looks like that, but when you write it, you're going to write it as an electron. Okay, so what particle is going to be left? Well, we still have 14 nucleons. Okay, so we're going to have 14 at the top, but now we're going to have 7. We have 7 minus 1 gives us 6. That's how we figured out it was going to be a 7. We need the charge conserved on both sides. It's the law of conservation of charge. Whatever charge you start with, +6, we need to have +6 on the other side. And again, we saw what was really happening is that a down quark flipped to an up quark to turn a neutron into a proton. And this brought it onto the band of stability. The last one we want to try was our beta positive. This, as we said, was an example of antimatter. And it turns out that lots of particles give off antimatter, including oxygen 15. So oxygen 15 gives off a positive electron. Again, it's called a positron. The symbol again is beta positive. Okay, the beta with a plus sign on it. And then the new element would need 15 nucleons, 7 protons, and that once again is nitrogen. Okay, so we work our way through with the rule being that the numbers on the bottom have to add up and the numbers on the top have to add up. The left equals the right for the bottom, the left equals the right for the top. Okay, so hopefully it'll be pretty easy. Again, you want to recognize the symbols. Alpha, that's a 4-2 helium. A beta negative, that's a 0, -1 electron. And a beta positive is a 0, +1 electron. And again, with this one, an up quark turned into a down quark to turn the proton into a neutron and bring us onto the band of stability. We learned about gamma. I showed you the symbol for gamma the other day. Gamma has no mass, no charge. So gamma, although it might appear in a reaction, doesn't really change what the isotope is. It just takes away some of its energy. Okay, and that's where we're going to end. I want to teach you guys about neutrinos and some other things, but we'll do that in our next lesson.